Okay, so good morning officially. My name is Pagliara. I think you know me already, and this course will be about statistical mechanics. It's let's say introduction to statistical mechanics. Actually, that is basically the aim of this course is to provide some general information, general tool about statistical mechanics. We are not going to explore a very complicated topic. Well, we will touch some of the most modern topics in statistical mechanics, which are phase transition in particular. But basically, the course is organized as follows. First part will be about, so let me see if you see something from the blackboard. Now, you might think that you are already expert in thermodynamics because you have done it during the first course of the university. But there are some topics that I would like to cover, which are not usually covered during the first year. For instance, first order phase the thermodynamical description of first order phase transition, for instance, Maxwell constructions or Gibbs potential, Helmholtz free energy. So the thermodynamical potential usually are not treated during the first course of this area. But when we will do this, you can stop me at some point and tell me, okay, we know this better than you, so that I can go on and switch topic. But this is the second year I'm doing this, and I think that the topics I was analyzing last year were mostly unknown for the persons who studied here, because during the first year you basically see the first principle of thermodynamics, the second one, and you don't see usually the thermodynamical potentials and other topics that we will try to cover, which are important also. Thermodynamics is not something old, actually. In some respect, it's it's still a very active topic because there are many research areas in which thermodynamics is playing a major role, such as, for instance, the study of heavy ion collisions, of course, or astrophysics, because we are always talking about systems which are macroscopic systems. You can think about a star, of course, as a macroscopic system, but also two heavy nuclei that collide actually form a kind of system which can be described in terms of thermodynamics, at least at some stage of the evolution of the system. So it's still a very important topic, okay? Now, of course, thermodynamics has a limited range of applicability, in the sense that, strictly speaking, one can use thermodynamics only for systems which are at thermodynamical equilibrium, which seems like a tautology, and I will explain what thermodynamical equilibrium is. And actually, the foundations of thermodynamics is in the statistical mechanics that provides a microscopic derivation of thermodynamics, as we will see. Okay, so the first, let's say, 2 weeks, I will remind you some of the most important topics about thermodynamics, and we will introduce something new, which are the empirical descriptions of first order phase transition. Okay. Second, then we will come to statistical mechanics, and therefore we will have a part which covers the standard topics, which are the ensemble, so ensemble theory. Which means classical ensemble theory and then quantum ensemble theory. which means the microcanonical ensemble, canonical, and grand canonical. Which is basically the heart of statistical mechanics, this ensemble theory, and we will see the difference between these different ensembles. Okay. Well, actually, before coming to this, so to the introduction of statistical mechanics, I think we will do something in between here. That will be Boltzmann transport equation. Why? Because thermodynamics is something which is defined, strictly speaking, on thermodynamical equilibrium, and ensemble theory can actually somehow go beyond the thermodynamical equilibrium because it provides some tools to explore also which is the response of the system to some external perturbation, a linear response theory. But in between, there is something, there is a big question: how does a macroscopic system proceeds towards the thermodynamical equilibrium, which is not a trivial question. So we know that, of course, systems try to tend to this thermodynamical equilibrium. The way they do it is described, at least in some specific scheme, with some specific assumption, by an equation, which is a very complicated equation, which is the Boltzmann equation, that describes how a system approaches the thermodynamical equilibrium. Also, this topic here is very fashionable recently, because this equation here is also applied to, for instance, the matter that is produced in heavy-ion collisions. Okay, so this is physics of Alice. So experiments like going on at CERN. Okay. Now, okay, from this we'll actually jump to this for, let's say, a couple of hours, maybe, or maybe a little bit more. Then we come to the ensemble theory 3. Quantum statistics. Quantum statistical mechanics.
Scusi, professore.
Sì?
Se scrive troppo in là non vediamo.
Ok, let me see. Grazie.
Grazie.
Opla. Dico, cosa c'è dietro? Non c'è niente. So, okay, actually, I can use up to this part of the blackboard. Ok. Perché se è troppo inclinato credo che non vediate lo stesso, no? No, qua perché ci sono questi... Fino a qui vedete?
Sì, ma verso la fine non mette bene a fuoco, la parte più lontana.
Ok. So, okay, let me raise this. Sì, qua si vede, penso, sì. So, third topic will be quantum. Statistical mechanics. And in particular, we will see here how, well, the major role of quantum mechanics here in statistical mechanics is played by the exclusion principle. Well, actually, before coming to the exclusion principle, to the property of the symmetrization of the wave function. So you know that a wave function must be symmetric or antisymmetric with respect to the change of two particles. And this will lead to very important modification of statistical, also of classical statistical mechanics. And with a correction that we will see is called Boltzmann counting. And also, of course, will provide the two most important distribution, which are the equilibrium distribution of quantum particles, which are the Fermi-Dirac and the Bose-Einstein condensation. So about this topic, of course, you know what a Fermi-Dirac distribution is probably, because you have done it last year. Okay, Bose-Einstein probably yes, also because you have done the black body in several forms. So for sure, I will not analyze the black body because I think you are overloaded by the black body physics. I will not probably discuss about the Fermi-Dirac. You probably know what a degenerate gas of fermions is, in the sense electrons in a metal. You might know something about that. So I think that last year I've done concerning the applications of the statistics, I've done the Bose-Einstein condensation, because I usually, so I think it's not usually covered, or if you have done it, you will tell me what is the Bose-Einstein condensation, which is also very, well, fashionable topic, because people are doing experiments about this, Nobel Prizes, etc. Whereas for what concerns the Fermi-Dirac distribution, I will probably derive the Sommerfeld expansion, which is the, let's say, first order with respect to a temperature correction to the ultra-degenerate gas. Okay, so we will see, let's say, a few applications that you have not seen yet, most probably. Okay, and if there is time, we will try to do we'll try to explain what is the Landau diamagnetism, for instance, but we will see. Depends on the time, and also this year, talking with the mask, I think, will slow down the process. And maybe we will also see something about maybe the Chandrasekhar mass as an application to astrophysics. But maybe some of you maybe have seen already this, in the sense that the Fermi degeneracy pressure is so strong, so important, that some stars, like white dwarfs, are stable just because of that. Okay, so just because of the exclusion principle, if you want. Okay, so it's a fantastic way in which quantum mechanics and the law of quantum mechanics actually will have a consequence to a macroscopic object, a star. So it's something still quite amazing. Okay, so this is quantum statistical mechanics, and then I think we will come to the last topic, which will be critical phenomena. Now, about these, one can do a full course just on critical phenomena, because it's a very rich and complicated subject. About this topic, you have seen something. Some of you who attended the course of complex systems by Lele Tripiccione. Did some of you attend this course? You? Next year, okay. Now, this will cover some topics which are within the critical phenomena physics, spin glasses, Ising system, and so on and so forth. But now, since we have, for the second time now, for the second year, a course on statistical mechanics, I will try to cover here the basic stuff. So like the Ising model in 1D, 2D, etc., the mean field, approximation, and so on and so forth. And I feel that next year, when you will follow, well, some of you will attend the course of Lele Tripiccione about complex systems, you can assume that some of the stuff I'm talking about were already done during this year, okay? So you can modify a little bit the program in the sense that, for instance, the Ising model, at least in some cases, will be analyzed during these lectures, okay? And I think this is more or less the program, well, the structure of the course. Now, a few suggestions about the books. About the books, I mean, there are many books, and now I think I remember just the name of the authors, and not the title, but the titles are always like, I don't know, statistical mechanics, statistical physics, and something like that, okay? So there is a book, let me see. Anyway, these info are also present in the page of the course, okay? So now if I do not write the name correctly, because I don't remember, you can find the info on the web page of the course, okay? So there is a book which is a very big book and complete by Patria, I don't know how to pronounce it, Statistical Mechanics. You can find it in the library, okay? It's a very big book. Second, let me see. Yeah, okay, there is Kerson Wang, of course. Now, Wang, there are two books. One, which is the introduction to statistical mechanics or statistical physics, something like that, which is recent. And the other one, so this may be, I don't remember, maybe, well, let's say recent, a very recent book. And then there is the classical one, which is statistical mechanics, which of course is much more advanced with respect to this one. And some topics will be taken from this book, whereas some other topics from this one. Okay, so but you can have a look to both of them. For sure, there are copies of this one in the library, and I think also about this one there should be a couple of copies. Okay, if I remember correctly. Now, for instance, in this book is one of the few books in which you can find the full derivation of the Onsager solution to the two-dimensional Ising model that we will not cover because it will take, I don't know how many hours. It's a very complicated derivation. But you can find in this book, for instance, if you are curious about that. Another very nice book, which is old, but still very nice, is the book of Kittel, and this is called the game Statistical Mechanics or something like that, okay? It's a very nice book. Small and compact, but very nice. 4. Now, when it comes to statistical physics, of course, the Russian school is the most prominent. So you might have a look if you are curious. To the books of Landau, Lipschitz, but now I'm sure I will not remember how to write Lipschitz. Something like that. Okay, so there are two books about Landau Lipschitz. You know, no, the series of books of Landau Lipschitz, I guess. You have seen already them? Yeah? No? Okay, so if you look for them, so these are very, very classical books in physics, in every kind of physics, okay? So they know everything. And specifically about statistical mechanics, these books are very important actually, because if you take one of the exercise of this book, you can still write a paper out of that if you find the solution. So there are some problems which only Russian can solve, and if we solve them, maybe we can publish a paper. So I mean, these are very important books. Okay, again, about statistical mechanics. There are two of them. One, well, two books. Anyway, I don't remember now the name exactly, but there are two books about statistical mechanics. First part and second part. And I think more or less is over about the books. I don't think that I can suggest some other. Yeah, I think that's it. Now, if you want to have a basis to study, I would probably suggest this one, okay? Because it's a compact book, it's very small, compact. And to consider, for instance, this one and this one as a more complete derivation or more complete book, okay? Again, these and these, they are very short, very compact, but they are very clear. Sometimes, however, the derivation are not complete, are not fully understandable, and maybe one could have a look to these other two books, okay? Whereas this one is something that you must have in your library, and if you have, I don't know, half an hour in which you, you have some doubts, you can, of course, have a look to these books, but it's not something that I would suggest to consider as a book to study for this course. Just to consult this book for some topics if you want, if you are curious. And another thing, of course, now we are in the age, in the area of lectures on YouTube. So I can also suggest you, apart from my lectures, if you want to see something more advanced, you can maybe have a look to the lecture of in this card. Who is a professor of statistical mechanics at MIT. And there are the lectures, I think the name is Kardar, if I remember correctly, lecturing at the MIT. So why not? I mean, you can also have a look at this if you like it. It is YouTube, YouTube. Now, concerning the way we do the exam, so last year we end up with COVID, and so at the beginning I was thinking to do an exam which was done in the following way. So a written exam, very short, and an oral exam as usual. At the end, the COVID came, and somehow the organization, the course started later, and there were many problems. So at the end, last year, the exam was just oral exam, okay, online, by the way. Now this year, let's see. So let's start, but we will see. But maybe the idea would be to make a sort of mixed exam, in the sense that we can do maybe a short written exam followed by the oral exam, as I'm doing now in the course of math at the second year. So like a very short, in the sense that there is just an exercise which must be very similar to the exercise we do here, to the applications we do here, and you will have something like 40 minutes to solve this exercise and then to access the oral. Okay, maybe something like that. I don't know. I will think about. Okay, For sure, we will not do a written exams of 2 hours, 3 hours, because this is basically impossible. Okay, we cannot do in presence, most probably also in June, and I'm not very confident in doing written exams of so many hours online. I don't like this. Okay, so we will see. We'll see how to do the exams, and it depends also on how many exercises we'll do it, and this depends on how strong I am talking with the mask. So if I get sometimes tired, so we will see. I mean, this is not important at the moment. Okay. So if you have any questions before I proceed, some curiosity or some I don't know, whatever question. Also from home, if you have any doubts, questions. No, okay. Now it's almost 12. Maybe we can do. Now let me proceed. Maybe 10 minutes more, if you agree, and then we will do a small break to get some oxygen and to take out the mask for at least 1 minute. So before coming to physics, well, and today I think I will do this, and then maybe we start with thermodynamics, but I'm not sure. Let me just make a few remarks on some mathematical tools that we will use during this course. Okay. So one of these is the Stirling approximation. You might remember what the Stirling approximation is, maybe. Some of you remember what it is? If not, don't worry, we are going to do it, okay? You remember?
The factorial.
Yeah, okay. There is a way to approximate the log of n factorial. This is something that will occur many times during the lectures, so that's how I prefer to do it once, and then we will use it many times. Okay. Now, usually n is this small n refers to the number of particles, for instance, or to the number of states, and usually there's a very large number. Okay, number of particles order of 10 to the 23. So usually n goes to infinity. And one can show, and I will do some, provide some arguments for this, that in the large n limit, the log of factorial can be approximated by the following expression, which is n log n minus n. Okay, so there is a leading term, which is n log n, which will dominate a large n limit. Okay, but we will use this expression. Now you can find in the books also some other terms which are subleading, but for what concerns us, we will limit to this approximation. Okay. Now, a motivation for that is the following. It's a very short motivation, so that's why I'm doing it. Now, the log of n factorial is the log of 1 times 2 times 3 times 4, blah, 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 times n, which of course can be written as a sum of log, no? Actually, this is a sum I1 to n of log of I. Okay. This can be also written as the sum from I1 to n of the log of I times, you still see delta I, where I define delta I to be 1. Can you still see if I write up to here?
No, non si vede l'ultima parte.
Non si vede. Ah. Cercando di scrivere largo. Ok. Così. Okay, so then I go here, okay? I try to go here. So up to here, you see?
Yes?
Yes? This one is not visible.
No.
This one is not visible. Okay. So let me move from here down here. So here I'm just saying that this is the log, so the sum from I to n of log of I times delta I, where I define delta I to be 1, just a number 1, just a number 1. Okay? Now, this expression here, what is exactly? If you think about what this operation is doing, is multiply the log of I times delta I, okay, and summing up. So if you have the this one, this is the logarithm, this is 1, this is 2, this is 3, 4, etc. So when I do the log of 1, 2, 3, 4 times delta I, where delta I is the interval between 2, 3, 3, 4, etc., it's like I'm doing an integral of the log, right? So this for large n, actually this can be, well, this is an approximation to the integral of the log, okay? So for large n, this becomes the integral from x to 1 to n of log x dx. Okay. Now this is something that we can do, because this is x of x minus x from 1 to n. This is the primitive of the log, right? And then, of course, this will see, you will see that is the n log n minus n plus 1, if you substitute n and 1, which, of course, for large n is actually just n log n minus n. Okay? So this is just a short derivation of the Stirling approximation. Well, it's actually argument in favor of this approximation. One can show it more formally. Okay, so since it's something that we will use many times, it's better to have it once and move on. Is it okay? Okay, there are no complaints, so we can proceed. Now, another thing that we will use is the gamma function. is the Euler gamma function. So we just we will not need all the properties of this function, but at least one of them will be useful for the microcanonical ensemble. So this is the gamma function. The gamma function is defined as follows. It's an integral from 0 to plus infinity of t to z minus 1 times e to the minus d minus t in dt. Now, in principle, one can define this function in the complex plane. Okay, but actually we will not need this. We just need the formula, this function, for the case in which this number here is a natural number. Okay, but there is a nice property that concerns this function, and it's the following. So if I compute the gamma of z plus 1, now the gamma of z plus 1 is this. If I just use the definition, is the integral from 0 plus infinity of t to z e to the minus t dt. Now I can do an integration by parts, and this is equal to t to the power of z e to the minus t with a minus from 0 to plus infinity, and then I have a plus integral from 0 to infinity of z t to z minus 1 e to the minus t dt. Okay, let me see if it's correct. T alla z, sì, alla meno t. Okay. Now, if this goes to 0, and we will discuss in a moment, you see that this term here is nothing but the gamma of z times z, right? Therefore, you conclude that the gamma. No, qua forse non vedete voi, no? No. Okay, so let me remove this. So the gamma of z plus 1 is equal to z times gamma. Okay, so it has this nice property, which actually reminiscent of the property of factorial. No? Because if you do n plus 1 factorial, this is n plus 1 times n factorial. And indeed, this gamma function is a kind of sort of generalization of the n factorial. Okay, so if you apply this to n, gamma of n plus 1, where n is a natural number, is n gamma of n. Okay, so it's a sort of generalization of the factorial, and we will use it when we will analyze the microcanonical ensemble. Okay, at least once we will use it. Indeed, for n at natural n, this is just the factorial function, okay, but can be generalized to z belonging to c. Okay. Indeed, if one tries to do the computation, the gamma 1 is 1. You can just remember which was the expression. The gamma of 1 is the integral from 0 to plus infinity of e to the minus t dt, and this integral is 1. The gamma of 2 by using this formula here is again 1. Gamma of 3 is 2 times 1. The gamma of 4 is 3 times 2 times 1. So you see basically that this gamma function, when n is a natural number, is just the factorial. Okay, and but is an integral expression of the factorial. That's why it's useful, and because we will use. We will find this integral at some point, and we will see that this integral is actually a factorial. Now, if you want some derivation, if you want some motivation for which the integrated part is 0, well, when we have done the integral, we had minus e to the minus t to the power of z, where z is a complex number. Now z can be written as a plus ib, and for sure, if z, well, actually this can be written also as minus e to the minus t, e to z log of t, which again is minus e to the minus t, e a plus I b log of t. Now, at infinity, of course, this integrated part goes to 0 because of the exponential. When t approaches 0, instead, it goes to 0 only naively if a is a positive number. Otherwise, one has to do some more complicated stuff. But at least for a positive number, and of course this is the case in which a is a natural number, this integral is 0. Okay, so this goes to 0 if a is positive. Okay, now of course I will not ask you this at the exams, okay, so don't worry about this. Okay, we just need this property of the gamma function. That's it. And maybe maybe we will stop now, and then I will do the Lagrange multiplier technique, so that we will finish now with this mathematical intro. Okay, so let's stop for 5 minutes or so. Okay.
Stavo pensando. Sì, ma perché Thermodynamics dovevo studiare. Prima di tutto. Sì, esatto. La cosa di sì, la migliore dei sistemi termodinamici. Dimostrava il potenziale di Gibbs che ha pazzo. Grazie. che lasciamo su Marte e mi dicono questo aspetta di cioè, questo adesso raccoglie le provette e te le lasci lì, ok? E tra 10 anni la NASA devo mandare della gente su fondamentalmente prenderle. Aspetta 10 anni che ci mandi le aziende e non mi fanno però... Ah, tu dici, non direttamente loro, ma non nel senso, mi sembra sempre la corsa bella, che però c'è un po' più di tempo. Il fondamento quello in cui vedi che c'è proprio un microfono dove ci sono arrivati.
Okay, so this was the integral representation of the factorial that we will see will apply at least a couple of times maybe. Now another technique that I need to refresh is the methods of Lagrange multipliers that you have done probably, what, analisi 2 maybe. You know what they are? Okay, you know? Okay, I will just remind you how does it work. Now the thing is that we need to maximize or minimize a function of multivariable function, but with some constraints that must be fulfilled. Okay, this is the problem. Okay, so you want to maximize a function f of x, where x is a vector of, let's say, n components, but under the constraints that, for instance, a function g of x is equal to 0. And then the problem is to maximize or minimize f of x with the constraints, or under the constraint g of x is equal to 0. Now, usually the way you do it, so to maximize a function, you take the gradient of f and you impose the gradient is equal to 0, and then this will provide maximization or minimization of the function. But now this time the complication is provided by the fact that there is a constraint that must be fulfilled. Okay. So when you write gradient of f, gradient of f scalar dx is equal to 0, actually this dx cannot be arbitrary, because I must check if g of x is equal to 0. So I cannot move freely in my volume, because I must be sure that this constraint is equal to 0. Now, this constraint equal to 0 means in particular that dg, which is equal to the gradient of g scalar dx, must also be equal to 0 if the constraint is fulfilled. Okay, now these equations is telling me that dx actually must be tangent to the surface determined by g of x equals 0. So let me be more clear. An equation such g of x equal to 0 is actually a surface. It defines a surface, right? So I think about a function of two variables, of three variables, and you impose a constraint, so you will have a kind of surface, okay, determined by this equation. And the gradient of G is a vector which is a point in every point is orthogonal to the surface, right? But this is a kind of surface of level. Okay, so now, so let me write here, gradient of G is orthogonal to the surface described by the equation G of x equal to 0. Now, since the gradient is orthogonal to the surface, this equation now is telling me that the gradient of G is orthogonal to the x. But since this is orthogonal to the surface, that means that the x is tangent. Okay? The x is tangent to the surface G of x equals 0. Therefore, when I want to maximize or minimize my function f, dx cannot be arbitrary, but must be a variation which is tangent to the surface G of x equal to 0. Okay, so now the minimization or maximization, sorry, must be computed by imposing that df, which is the gradient of f scalar dxt, exportable, sorry, is orthogonal dx, must be equal to 0. Okay? So when I want to maximize or minimize in presence of a constraint, what I need to solve is that, let me write it here. So first of all, let's introduce dx in terms of two components, dx orthogonal plus dx tangent. Okay, the first one is orthogonal, and tangent to the equation, so the surface described by the equation G of x is equal to 0. Okay, so therefore now I have an equation 1, which is telling me that the gradient of f scalar dx, sorry, this is not orthogonal, but this is the tangent, of course, sorry, tangent equal to 0, okay? And of course, so let me remind you what was the derivation. So gradient of G scalar dx is equal to 0, since the gradient of G is orthogonal to the surface, dx must be orthogonal to the orthogonal of the surface, therefore the dx must be tangent. Okay, that's why here there is tangent, the x tangent. Okay, so this is one equation. Then I have also the gradient of G scalar dx tangent, of course, is equal to 0. Of course, this is trivial because we know that this is orthogonal to the surface, and if I multiply by a vector which is tangent, then I get 0 by definition. Now I can combine these two equations and say that if I take an arbitrary linear superposition of f of g, this must be, and I do the gradient, this must be also orthogonal to the x of t. Okay, so by combining these two, I can say that the gradient of f plus lambda g scalar dxt equal to 0, where lambda is a real number or a complex number in principle. Okay. Now I'm almost done. Almost done. So this equation actually now is there. Now we have some freedom to choose the value of this lambda, and in particular, I can select a value of lambda for which, so choose lambda, such as also the gradient of f plus lambda g scalar dx orthogonal is equal to 0. Okay, this must be true because of the reasons that I was explaining before. Now I have some freedom. So these are general, so a parameter that is not fixed. Now I can choose a value of this parameter for which the gradient of f plus lambda g scalar dx orthogonal is equal to 0. Okay. Now, if we combine this equation, let me call it 3, and this equation, let me call it 4. If I do 3 plus 4, I get finally that the gradient of f plus lambda g scalar dx is equal to 0, because dx is the sum of dx orthogonal and dx tangent. So at the end of the day, minimizing or maximizing a functional or multivariable function in presence of a constraint means that I need to compute, well, I have to solve this equation, this one. So I have to impose that the gradient of f plus lambda g is equal to 0, which of course means n equations if I have n variables. Now, when I impose this equation, I find a solution of this equation, which is a vector x, which depends on the value of lambda. Okay? Then, once I have x as a function of lambda, I can impose, I can find the value of lambda by imposing that g of x of lambda is equal to 0. Okay? And this will provide me the final solution. Okay? Now, we will apply this method many times, okay? But just to summarize, the problem is to maximize or minimize a function of several variables in presence of a constraint. What is this constraint? Well, we will see that this constraint is, for instance, the conservation of particles, can be the conservation of energy, or so on and so on. So the conservation of some physical quantity, okay? And we are always in presence of constraints. Well, actually, we will see that the more constraints we have, the more it's difficult to, let's say, find the minimization or the thermodynamical distribution, actually, we will see. And at some point, we will remove all the constraints because then computation is much more easier, okay? But when we will have some constraints, we will need to follow this procedure. The procedure is the following. You have to do the gradient of f plus lambda g, where g of x equal to 0 is the constraint. Find the solution of this equation, which is a vector, which is in general a function of lambda. And then to find the value of lambda, you impose that g of x of lambda is equal to 0. Okay? So this is the procedure we will follow. Okay, I think that this is enough for what concern the mathematical part. And now we can go on. And let me, are there any questions also from home? not let me introduce the notations once forever. So now this is statistical mechanics and thermodynamics together. So we will have for sure P, which is the pressure. Then S will be the entropy. And E, U will be energy or internal energy. The difference between these two quantities will be clear later on. It depends on which ensemble you are choosing. If the ensemble, well, if the system is isolated, so there's no interaction with the environment, the energy of the system is conserved, so then I can talk about the energy of the system. Whereas if the system is not isolated from from the environments, I can just talk about internal energy, which is a quantity that can fluctuate. Okay, it's not fixed. You can have some fluctuations. Well, then T, of course, is the absolute temperature. And let's call it A, the Helmholtz free energy. Have you seen already the Helmholtz free energy somewhere? Probably not, that's why I'm asking. Okay.
Professore?
Sì.
Scusi, la webcam è andata fuori fuoco, non si vede più.
È vero. Io non ho fatto niente, giuro. Adesso? Adesso si vede?
Non come prima.
Come prima. Ecco, adesso forse si vede, vero? Adesso io la vedo.
Sì, adesso sì. Grazie.
So, A is the Helmholtz free energy. What else? Then we have the Gibbs free energy, G. Gibbs free energy. Then we will indicate with capital omega to be depends on the ground potential but we will not mix these two concepts. Number of microstates. We'll call it omega. Then what else? We have B, which is volume. Then N, number of particles. And mu is the chemical potential. Pennarelli non si vede niente. Terribile. What else? I think it's almost done. andiamo al blu. Then Q, col blu si vede meglio forse. This is heat. Now remember that heat is not a property of a body, it's something that it's a kind of energy that is exchanged. So it could be heat released or heat which is received by a system, okay? And of course, dQ will be the infinitesimal heat, again, exchanged by a system with the environment, okay? I remind you that this is not a different, exact differential, okay? You might remember this, okay? As a, well, similarly, L is work, and dL is the infinitesimal work done by a system or which is done onto the system, okay? dL is equal to PdV only when you are talking about reversible transformation, okay? So this is for reversible. So infinitesimal work. I will remind you what a reversible transformation is, okay? And I think we have done with the letters. And let me go now to here. Now, so let's start with thermodynamics now. What is thermodynamics? Well, it's a way to treat the system, macroscopic system. By macroscopic, we mean systems made of a large number of particles. By large, we are always thinking about the Avogadro number. Okay, so we are talking about system with n of the order of 10 to 23 particles. So, of course, this is the kind of system which is considered in thermodynamics. And thermodynamics does the following game. So in thermodynamics, we are not pretending to describe these systems in terms of microscopic variables, such as the position and the momentum of the particles, of course, because this will be not only impossible, but actually useless. But we try to describe macroscopic system in terms of macroscopic variables such as pressure, volume, entropy, all the quantities that I was referring to before. And once you define these variables, thermodynamics establishes, based on some principles, of course, and some equations of state, establishes some relation between those macroscopic variables, such as I said before, temperature, pressure, and so on and so forth. The other thing that thermodynamics does is once you have an initial condition, under some constraints, under some conditions, it can tell you, thermodynamics can tell you what will be the state of the system after some transformation. It will not describe the evolution of the system, for instance, towards equilibrium, It will describe just the state of the system in equilibrium, in an initial equilibrium state, and for a final equilibrium state. What is equilibrium? Equilibrium has a very, let's say, let me write it down, thermodynamical equilibrium. What is thermodynamical equilibrium? It's a state. It has not a very, let's say, precise definition, in the sense that it depends on the time you are observing, on the amount of time you are observing the system. So the typical example is the glass. The glass of this window is in thermodynamical equilibrium, but actually the particles of this material are trying to go down. So if you observe this material in, I don't know, thousands of years, you will see that actually on a much larger time scale is not in equilibrium. But for what concerns our daily life, let's say if I observe the system here in 1 day or 2 days, 1 year, this is in thermodynamical equilibrium, in the sense that it is in a specific state, with a certain temperature, certain number of particles which is basically conserved, and so on and so forth. So the thermodynamical equilibrium means basically that during our observation time, the state of the system is stationary. So the pressure is fixed, the volume is fixed, and so on and so forth. Yeah, the internal energy is fixed. So that's the meaning of thermodynamical equilibrium, okay? Now, of course, thermodynamical equilibrium can be established if I introduce a perturbation. So if I take a system like this box, and I see that this box is in thermodynamical equilibrium, in the sense that it doesn't change its shape, is not burning, is not losing particles, nobody's pushing it. So it's in this definition of thermodynamical equilibrium. Now, if I do some perturbation, so if I try to squeeze the box, at some point, when this perturbation will finish, of course, you will reach another state of equilibrium. Thermodynamics basically can describe only what happens between the states of equilibrium. It does not have any dynamics inside. So I cannot describe with thermodynamics how from a state A I go to a state B in terms of dynamical evolution. I can describe it only in the case in which the evolution from a state A to a state B is done by following exactly thermodynamical equilibrium states, okay? Which is the case of reversible transformations. So now I'm repeating some concepts that you already have, and so I'm just repeating them. If you have any questions on that, we can talk about, okay? It's something that you have deeply inside you, the notion of thermodynamical equilibrium. But I will try to. So I'm trying to remind you what it is thermodynamical equilibrium. Okay. Another thing that thermodynamics does, well, another assumption, a simplifying assumption, is called thermodynamical limit. What is the thermodynamical limit? It's the limit in which the number of particles is large, 10 to the 23, the volume is large. Large with respect to what? With respect to the size of the particles, basically, okay? But the density of particles, this is maybe I forgot to introduce the variable density of particles, which is the ratio n divided by v, and this is finite. Okay, so this set of assumption is called thermodynamical limit. Number of particles going to infinity, volume also going to infinity, but the ratio between n and v is finite, the density is finite. Why this limit is very useful? This limit is useful because basically it doesn't, I do not have to care about the surface effects, right? So if I have, so let me write it in brackets, no surface or finite size effects. If you think about the volume here with a certain number of particles, now if V is very large and n is very large, the contribution of the surface to the total energy of the system is vanishingly small, okay? Because if the volume is large, basically I can avoid to introduce the complication related to the presence of a surface. So it's like being an infinite matter. So thermodynamics basically is telling me what happens here, okay? When I'm far away from the surface, the direction of the surface is not a matter of thermodynamics, okay? To make an example which is maybe more physical, think about the semi-empirical formula of the mass of nuclei. Okay, if you remember this formula, there are many terms. The first two terms are, one is related to the volume, and the other one is related to the energy. Okay, now thermodynamics takes care only about the volume term of this formula. Okay, it doesn't take into account the surface effects, which will need to, for which one need to introduce surface tension and so on and so forth. Okay, so the thermodynamical limit is this limit here. We are in infinite matter. We do not care about what happens at the surface. Okay, or if you want, we neglect the presence of a surface, and the surface does not play any role in the energetics of the system. Let me see if I told you everything about this page. I think it's done. Then let's introduce some names. Now, thermodynamics, of course, as all the branches of physics, has to do with some quantities that must be measured or can be measured. And so among these quantities, there are some of them which are called state variables. State variables. Which are the state variables? Well, for example, the internal energy is a state variable. The entropy is a state variable, etc. And what is the difference between state variables and, for instance, Q or L? Q or L do not refer to some property of the system itself. This is something that is exchanged by the system and another system. Whereas U as temperature, pressure defines exactly what the state of the system is, without any, without taking into account how the system arrived to this state. Okay, typically, one of the plane that one uses in thermodynamics is the PV plane, And what is a state is just a point here, okay? That we call state A, then a point here that we call state B, and each of these points, A and B, has a specific value of pressure, specific value of volume, of entropy, of internal energy, and so on and so forth. Okay, these are state variables. It defines the state of my thermodynamical system, whereas Q and L are not state variables, are just exchange of heat or exchange of work. Now, among the state variables, one has to introduce here the extensive and intensive variables. Okay, extensive variables are the ones that scales as the number of particles. So, for instance, internal energy is an extensive variable, entropy is an extensive variable, okay, and so on and so forth. Well, the volume, not the volume of two boxes is the sum. The total volume is the sum of the two volumes. Okay. What is the difference among extensive and intensive? Extensive scales as the number of particles. Intensive do not scale with the number of particles. Okay. So these are, for instance, temperature, pressure, chemical potential, density of particles. Okay, these are intensive variables. So if I have two boxes with the same temperature, the temperature is the same for both of the boxes. I do not have to scale. I do not say that the temperature is twice. Okay, whereas the number of particles is twice, the volume is twice the volume of one of the two boxes, and so on and so forth. Okay, so this is a very simple concept, but it's useful to remind you which are the differences between these variables. Okay, so let's move on, and just a couple of minutes. Just to play with thermodynamics, I will introduce, I will remind you one important thing, which is the equational state of ideal gas. And what is important for the moment is just to write down the notations. Okay, so ideal gas. Ideal gas equational state. Now, for instance, this equation that you will see many times in thermodynamics or in chemistry is an empirical equation. Actually, there were before the Boyle equation, the blah, blah, blah. I don't remember even the name. Now, there is a clear derivation of this equation once we introduce statistical mechanics. And basically, this equation corresponds to the assumption of having Hamiltonian, a microscopic Hamiltonian with just the kinetic term. Okay, we will see how it works. This is the most basic equation of state, which corresponds to the fact that particles, well, the interaction between particles is neglected. Then one, of course, can do something more, introduce some interaction, and we will see how this equation of state can be corrected once we introduce the interaction. Okay. Okay, so of course this is the ideal gas equation of state, where P is the pressure, V the volume, and number of particles, temperature, and this is the Boltzmann constant. Okay. Now, of course, the other thing that we will use many times is the first principle of thermodynamics, which is telling you that dQ is equal to dl plus du. So this is infinitesimal heat, infinitesimal work, infinitesimal change of internal energy, and dl is equal to pdv for reversible. Now, reversible transformations means transformations that occurs by following a sequence of equilibrium states. Okay, so typically one in general physics one does the following example. If I go to a state A, from a state A to a state B, and I can follow a line, each point of this line corresponds to a specific equilibrium, thermodynamical equilibrium state. Okay. Which practically corresponds to the fact that I'm changing slowly the condition of the system. So if I do a compression, for instance, if I slowly compress the system, following a sequence of equilibrium states, these are reversible transformations. Whereas an irreversible transformation, just a quench, a fast reduction of the volume of the box, for instance, will not have any representation in this diagram, okay? Because there's no sequence. The system does not follow a sequence of equilibrium states, okay? And those are the irreversible transformation, okay? Now you know that reversible is actually a myth, in the sense there are no transformations which are fully reversible. Just one can approach this limit when doing a very slow transformation of the system. Okay. Okay, so this is, of course, the first principle of thermodynamics, which basically is just the conservation of energy by introducing also the fact that a macroscopic system can exchange energy also through heat. So it's conservation of energy in presence also of the possibility of exchanging heat, you know? And of course, after the first principle comes the second principle of thermodynamics, which tells you that this we will see in several forms, actually. In the first form, for isolated system, by isolated system, I mean something which is here in a box, and there's no exchange of heat, no exchange of work, no exchange of particles from the system, between the system and the environment. Okay, so no heat, no work, no particle exchanges. What happens for isolated system? What the second principle of thermodynamics tells you is that the variation ds of the entropy is larger than zero. No? This is basically the second principle of thermodynamics in presence of isolated system. We will see that actually this way to formulate the second principle is very useful, but actually, strictly speaking, isolated systems are not very interesting, in the sense that most of the times the systems we are referring to are not isolated, but at least they are exchanging heat with a heat source. And actually, we will see that the way to formulate the second principle of thermodynamics is a slightly different way. Okay, it depends on the condition. Okay. Now, one thing that you might remember, and maybe on this I will, well, no, maybe an exercise is too early for the moment, but something which is related to the second principle of thermodynamics, and actually is the best way actually to formulate is the Clausius theorem. You remember what the Clausius theorem is telling you, maybe? Well, it can be formulated in several forms. One of the forms is that Vs is larger than Eq divided by T. Okay? Well, this is the differential form of the Clausius theorem. The integral form of the Clausius theorem is that dq dt integral minus less than 0, where these integrals means with the circle means cyclic transformation. Okay, these are both formulation of the Clausius theorem, where the equality holds true when we are in presence of reversible transformation. Okay, so let me write it here. Ds equal to dq divided by t for reversible, and the integral of dq divided by t is equal to 0 for, again, for reversible cycles. Okay. Now, next time we will see. I think I will just do an exercise to provide some motivation of this equation, but most probably you have done this, right, in the course of general physics, isn't it? Carnot cycles, you know that, right? Va bene, let's stop here and see you on next Thursday, I think. Ciao a tutti.
Arrivederci.
Arrivederci.